Okay, so by now you should have a good understanding or fundamental understanding of what CP is. And what I'm going to show you next is how to apply CP to improve the quality of the process. We're going to make use of this example. This is the picture is showing a house, but I was sort of like would like you to imagine that this is a factory. Okay, I just would like you to imagine this is a factory that producing different type of product. It's quite common that in a factory will produce more than one type of product. And for this particular example, these factories are producing 4 products. So there are 4 doors there. The house is so special that with 4 gates, which gates with different size. So the size of the doors representing the specification of the product. Example, door 1 representing product 1, and then door 2 product 2, and same go to 3 and 4. And different products have different design as well as different specifications. Example for product 1 or door 1 is the biggest among the 4. So example, assume that the tolerance is plus minus 10, a product with the biggest tolerance, followed by products perhaps 4 and 2, which is slightly bigger. Perhaps door 4 is bigger than 2, so as such, tolerance plus minus 8. Remember in the previous slide, previous video, we are saying that based on the tolerance of the product, you are able to derive the product specifications. And door 3 apparently is the smallest. So these are door of products. How to make these products? The products need to be made by machines and men. All right. So the plus minus 10, plus minus 5, plus minus 2, and plus minus 8 is so-called void of customer. So the product need to be made by machines. So in this example, the machines referring to the car. So car is the machines that producing the product. And the process of parking the car into the bagger or into the carport, you can't park it the same position consistently is because parking process will come along with variation, and this variation could be caused by the car itself, car representing machine and material. The variation could be come from the driver itself, wrong spelling, from the driver itself. So another source of variation is man, and the fourth variation is methods or how you're going to park your car into the garage. So we have 4 cars here with different size representing different car or different machines with various process variation, some with big variations such as car 2, some with small variations such as with car 3. All right, so each car has variations of machine, material, man, and methods. And let's see how car 1's going to park into door 1, or let's see how machine car 1 going to make products door 1. The process looks like very easy. It's because the gate size is much bigger than the car size. Or in technical term, we're saying that the specifications of product A is much bigger than the process variations. Hence, door 1's or car 1's, car 1 is able to produce a good parking process, or car 1 is able to produce a good product door once. Okay, why we say it's good is because the upper spec limit minus lower spec limit is much bigger than the variation of the process, which is equal to 6 sigma. How about car 2? Car 2, the size of car 2 look exactly same as door 2. So machine car 2 still might able to produce product door 2, however, it very much depends on the operator skill perhaps. Okay, and this process, if you look into the process capability, perhaps the specifications or the size of the gates, the difference between upper and lower specs is almost similar to the process variations. Therefore, the CP perhaps is equal to 1. As for car 1 and door 1, CP definitely is more than 1. How about car 3? Car 3 apparently it looks like much smaller than door 4. Theoretically, car 4 should be able to park into door 4 easily, or machine car 3 should be able to make product door 4 easily. If this will be the case, take a look on how car 3 park into door 4. Remember how door 4 is the second biggest gate. Not really, you see. Even though car size is much smaller than the door size, even though the machine capability, the machine variation is much smaller than the product specification, there's also a possibility that the machine not able to produce product with good quality because their variation, such as in terms of variation in terms of driver, man, or in terms of methods of the parking. Okay, so how about the CP for this scenario? Car 3 to door 4, CP definitely will be still more than 1. That's because the door size is much bigger than the car size. And however, the process is produce defects. So this scenario is different from door 1 and car 1. Right. How about car 3 and door 3 and car 4? Theoretically, car 4 should be able to park into door 4 easily because the car size is much smaller than door 3. Or the machine's variation is much smaller than the product specification. However, there's also a possibility that even though there's no defects, the car didn't hit the gates. However, there's a possibility that the car didn't park at the position that it's supposed to be. So that's another scenario. So why explaining this? This show you problems of a very common problem in factory in the allocations of machine or selections of which machine to produce what products. So if the selection machine is done incorrectly, there's a possibility that a machine with bigger variations might be chosen to produce a very precise product. So to avoid this, we can apply process capability as an index or as a guideline for machine allocations in the factory. This could be done by CP and another index that Cpk we're going to discuss later. Now look into the first index, Cp first. Okay. Let me adjust the slide. Just bear with me. I adjust the slide for a short while. Okay, we're going to use this slide to continue our discussions. So I'm saying that this is a very common problem happened in factory. Wrong machines being assigned to a wrong machine be assigned to produce a product. Machine with higher capability produce bigger tolerant product. So how to resolve this problem is by generating an index that we have learned so far, Cp. So what is a common problem that will be faced in the factory? Take a look on this. Take a look on this scenario. If you ask me to do allocations of machine to product, remember machine we're referring to the car, and then product is door. So perhaps I will start allocating machine 2 or car 2 to produce door 1. I will ask car 2 to buy door 1. Why? Is because car 2 is the biggest car. Then door 1 is the biggest door. You get me? So I'm allocating machines with the highest process variations to produce a product with the biggest tolerance. That perhaps is what I might do first. Okay, take a look, continue the slide. I might pick this. Car 1, car 2 to produce door 1. But after this, how about machines 1, 3, and 4? They look quite similar in terms of size. Car 4, should I assign car 4 to produce door 4? Should I? Or should I assign car 1 to produce door 4? This decision is tough. Why? Is because as compared to the previous allocation, the first allocations were allocated car 2 to produce door 1 was based on the concept of car 1 is the biggest, so we should park at door 1. Or car 1 is a machine with the highest variation, should assign to produce product with the biggest tolerance. But we come to the subsequent machines and product allocations. We really can't sort of like ensure that the allocation will be the best, simply based on the tolerance. So how are we going to do that? Example, car 2, example, car 3, car 4, and car 1. Which car that should assign to door 4? I can't give a very, the picture itself can't give a very clear picture. Therefore, we need to apply an index that will help us to do allocations. And that index is with the name of process capability index. And we had discussed the first process capability index earlier with the name of process potential ratio. I know we repeat. The thing to take note here is CP, we want CP that more than 1. And then traditionally we want CP more than 1.33. At least 1, but must be more than 1.33. Why? Is because you see, if this is your bar graph, let me try to draw the bar graph. CP must be more than 1. But if this is the bar graph, and your power plot is too close, it's between the bar graph, however, very close to the bar graph, CP itself will be still bigger than 1. However, it's too close. It's too close. So statistically, we prefer CP that targeted CP of 1.33. Okay. Sigma, you can get sigma from SPC that we learned 2 weeks back when the process is constant in statistical control. You can use the CP. If you don't have a SPC put in place, you can calculate sigma based on what you learned in statistics. This is how to get sigma. And in fact, we have discussed this in the example that showed earlier. The wider the gates easy to park. This is CP1. And another example is the gate is double of this. This is CP1. The gates and the variation is the same. CP2 is the gate is double the size of the variations. So in short, CP the higher the better. Okay, this is CP2, and this is a summary of the indications of CP index. If less than 1, then it's very poor. 1.0, 1.5 is general. And then what we targeted is we want to have a CP of more than 2.0 or 6 sigma process. Why? Why we say 6 sigma? We're going to discuss 6 sigma more detail in the subsequent topics, subsequent topics, correct? But in short, when we say a process is 6 sigma, it means that when we are producing 1 million products, 1 million products, the possibility of defect is only, the number of defects is only 3.4. We produce 1 million products, only 3.4 of the product, there's a possibility that might be rejected, which is quite great. That's the reason we aim for 6 sigma. Okay, 3.4 parts per million. All right, so we have discussed this, and I'm going to show this. So this is CP. Therefore, 6 sigma quality requires CP of 2.0. Okay, we want CP of 2.0. Okay, we got 2.0. CP of 2.0 reflecting, more than 2.0 reflecting 6 sigma process. And 6 sigma process is a process that only will be only cost 3.4 part reject of million. Okay. However, there's one problem of CP. CP does not look at how well the process is centered in the specification rate. What does it mean? The last sentence in the slide. CP does not look at how well the process is centered. If off-center, if a process off-center, or before that, there's a mistake on the subtitle here. The title here should be process potential ratio, not process capability ratio. Process capability ratio is CPK. Take notes. All right. Okay, capability more than 1, CP 1.33 targets, and then 6 sigma 2.0. 6 sigma CP is 2.0. So we always want to aim for more than 2.0. So the weakness of CP is doesn't consider off-center scenario. What does it mean? Look at this, the next one. It's like, okay, this is the first one is both are CP2. Remember, CP is comparing, CP is only comparing the, this is like scenario number car 3 to door 4 lah. Quite similar to scenario of car 3 to door 4. Comparing the car size and the gate size, it look great. Okay, car is smaller than the gate, and then you calculate CP, CP was also more than 1. However, the car hits the gate. So how to address this? We're going to address this by using another process capability index with the name of CPK. Okay, so this is CP. The first scenario, the gate is double of the size of the car. So when you park your car in, definitely CP will be CP. If we compare the parka and the car, the first picture here, the parka car is 1 example, the parka is 2. So therefore, the CP will be 2 divided by 1, so equal to 2. The second scenario is the same. Parking gates is 2, car is 1, CP also equal to 2. However, in the second scenario, in fact, the driver parked the car at the neighbor's house. So this graphically representing what I discussed earlier. Both scenarios are with CP2. So, but the second scenario is off-center. So to address these problems, to address the weakness of CP, which is can't address off-center process. There's another process capability index that we call it CPK. Okay, CPK take into consideration the means of the data. So what CPK does is instead of finding the difference between spec limit, CPK finding the difference between upper spec limit and the means of the data that you collected and divided by 3 sigma, as well as the difference between the means of the data with lower spec limit and divided by 3 sigma. And among these three numbers, CP will take the smaller one or the minimum. By doing that, CPK take into consideration the means of the process. So in the first picture, the means of the process is the centers of the specification. In the subsequent process, the means of the process is offset and beyond the spec limits. So we take example of the second case. Maybe let me change the color. We take example upper spec limits minus x bar. X bar is the means of the process. For the first case, the difference between upper spec limits and means of the data is as what shown in blue color line in the slide here. Okay. However, in the second case, the difference between upper spec limit and x bar appear to be shorter than the first scenario. Okay. Therefore, the second process potentially is going to have a lower CPK. Okay, and that is the reason that by taking the considerations of x bar into the calculations, CPK able to resolve the off-center analysis for process capability study. Okay, so besides CP, we have CPK. Okay, and CP without that into consideration of the center of the data, but CPK does. Okay, and that's explanation of CPK. Okay, CP does not take into account the closeness of the mean to the target. Okay, therefore CP is insufficient. We need another one called CPK. So sometimes the car could make it, sometimes cannot. Why cannot? Is because of the 4M. So we need another index called CPK. This CPK 0. CPK 0 means the center of the data exactly on the the limit. It could be the upper control limit or it could be lower control limit. Okay. So CPK 0 means the center of the data, the mean of data is same as the upper spec limit or lower control limit. Then means is CPK 0 car will exactly hit the tiang. Then subsequently 0.5, slightly better, but still not the best. CPK 1, you can park exactly into the car park. And this is the formula. And the thing that I didn't mention earlier is the sigma, instead of using a S as a short form for sigma. And okay, let's stop for short one. Something that we missed. Okay, back to here. Okay, there's one thing that I didn't mention earlier. The upper spec limits minus the mean divided by 3 sigma is we call it CPU. Okay, means process capability based on upper spec limits. And if you calculate CPK based on the difference between mean and lower spec limit, then the index we name as CPL. Why I want to highlight now is because when you're going to do your mini test, these two numbers will appear. You must know. If not, you don't know what are these two, CPU and CPL. All right, continue. So sigma using S. Okay. Then these are the graphics showing the difference. The first graphic basically CPK equal to CP, and the second is basically the mu have been offset. Therefore, CPK will be smaller than CP. And the third one basically is quite similar to the second one, but it's even is further, much further than the target. Okay, the mu is quite the target. Okay, but what is important for us to know basically is for CP we target to have 2 and above, and CPK 1.5 and above in order to declare the process as a Six Sigma process. Okay, so CP2 and CPK 1.5. And that's our target. Look at this scenario. There are 4 scenarios here. Out of this 4 is only one process that able to reflect a good process capability. I suppose I ask you, but I'm not able to answer. So this is the one. The other 3 are process that showing whole CPK. For this case, the case that I'm pointing now, the result is very straightforward. Just shift the means. The variation looks still alright within the spec limits. And for the first case that I'm pointing now, to resolve, to improve the CP here, the process capability here, the action required is to reduce the variations. The most difficult one will be the case that I'm pointing now. We have a problem of off-center and also big variation. So to resolve this, you need to shift the mean into the center. In the meantime, you also need to reduce variations. So this is a way that how you're going to study your, okay, I stopped short while. This is the way that you're going to interpret your results of your task 2. So bear in mind. Okay, I don't think that you're going to get this result. You're going to get one of these. So interpreting, you can interpret in this way. All right. There, what will be the next? Interpreting CPK. Yeah. More than one, but we want 1.5. Yeah. All right. Why we are learning this CPK? Why we are so like studying CPK? Number one, as I mentioned earlier, is for machine allocation. Based on CPK, you can allocate. You can make sure that you have combinations of machines and products that every single combination able to achieve a CPK level that's your targeted CPK level. Okay, this is one thing. So the first objective of learning process capability is you can make use of CP or CPK, preferable CPK, because take into consideration of center. You can make your CPK to analyze the machine allocations against product to make sure that all the combinations of product and machines are able to achieve a CPK, a desired CPK level. Okay, why I didn't quote any number, I said desired CPK level, is because different companies have different targeted CPK level. And in this module that we discussed now, we are aim for CPK that more than 1.5, and we aim for CP that more than 2. This is the first objective. The second objective is we have learned hierarchies of quality improvement methodology, inspections, SPC. But so far, nobody asked me when we should do 100% inspection, when should we do sampling inspection, when should we purely do process control, or when we should stop inspections. Okay, so this answer could be addressed. These questions could be answered by CPK index. Okay, so what I mean is by plotting the CPK, by calculating the CPK, if the CPK number is less than 1, means have no choice, you have to do 100% inspections. If the CPK is between 1 to 1.5, you have to do acceptance sampling and SPC. And if your CPK is more than 1.5, 6 sigma process, 3.4 defect per million, then I'm going to say that no inspection required for that process. That's another reason that why we want to know, we want to learn CPK. All right, so the next slide will be, if CP and CPK is so important, so how am I going to improve CP and CPK? Both are the same. You see how to calculate CP, CPK is to compare the spec limits, and in CP we take in consideration the mean, to compare the spec limits versus the variation of the process. So if I want to improve CP and CPK, there are only two variables I can pair around. Number one is I have to control the spec limit. Number two is I have to reduce the variation, widen the spec limit, and reduce the variation. These are the two only ways that I can improve process capability. There's no other way. Reduce variation means look into the 4 M's. Therefore, if we talk about how to increase CP, CPK, if we know CP is 2, and we want to set a specification based on a known sigma, then we can do that. Stop short one, go back slightly. I'm not yet finished. Then the slide end. I'm saying that. Okay, let me start in here. Okay, here, good. I'm saying that you see, the only way to improve CP is refer to the formula. Same thing applicable to CPK. The only two parameters that you use to calculate CP or CPK, one is the specification, another one is the variations of sigma. So CP and CPK, the higher the better. In order to have a higher CP or CPK, there are two options that we can do. One is to have a higher CP and CPK, you can increase or widen the specification limits. Number two, to increase CP or CPK, you can reduce the variation of sigma. Okay, so meantime, if I have the targeted CPK, example, you have targeted CPK of 2.0. Why 2.0? Because 2.0 is a 6 sigma process. If I have a targeted CPK, scenario number one, perhaps I want to fix my specification. Some of specification given by customer, I got no choice, I have to fix the specifications. Then the next thing I'm going to do is I must calculate what is the variation what is acceptable variation of the machines that allow me to produce the product within 6 sigma level. You get me? I got the spec, I got the CP, calculate the sigma, and that is the sigma that you should control. You try to reduce the sigma of your process, the variation of process, by studying the 4N until you reach the level that you calculated. That's one thing. Another thing perhaps is, another way is perhaps CP is 2, and you know that the machine that you're using is old machines to calculate the variations, quite difficult to improve. Since you have CP, you have the variation, can calculate what is the spec limit. The spec limit that you calculated carry a meaning that that is the process, or that is a product specification that able to be done, to be carried out by these machines. You get me? I got the CP, I got the machine variation, I calculate the spec limit. That spec limit carry a meaning of this is the spec limit that can be produced by this machine in order to achieve 6 sigma process. All right, okay. Then by saying so, I think this will be the last slide that I'm going to explain subsequently. Is that repeating that what I have explained earlier? What is process capability? Okay. What else? Let's look at the next slide. The next slide is important. Some common mistake. Some common mistake perhaps that when you do CPK or CP is unstable process. Process must be stable. From SPC, we call it must be statically in control before we talk about calculating CP, CPK. If not, if statically out of control, you can't. Second, the data must be normal. You done it in your task 1. You should have done it in your task 1, using Minitab to make sure that data is normal. Specifications are not meaningful. The specification is too tight. Okay, it's too small. Or the specification is too big, it's meaningful. Example, too small, 0.01. No, look into spec first. People look into what's that? CP, CPK. Using too small set data, if you take n equal to 10, no, the data is inaccurate. 1, 2, 3, 4. Number 5, index when not independent. 50 data you want to collect, but that 50 data you collect in 10 minutes. You get me? You ask one student drive 1 car, park 30 times in 30 minutes. Means all the data is not, all the data are correlated, or all the data are correlated, so not accurate. All right, so this will be the last slide that you need to do a tutorial. These tutorials, I think, quite straightforward. If you understand what I explained earlier, you should be able to do this. The tutorial requires you to calculate the process capability for the ball bearing production process, the specifications and the sigma, the variation is given. Sigma is standard deviation, right? If given, you can calculate. Then you can propose how to improve. And what value standard deviation do you? Okay, I'll let you try first. So by saying so, we have sort of like done the topic of process capability.